Okay, this is section 7.2, matrix algebra. We're going to talk about a matrix, and then in section 7.3, we'll use that to solve systems. So, matrices. The first thing we need to do is talk about naming them. This is considered a 2 by 3. It's always rows, columns. Columns are the vertical one, and it's number of rows by number of columns. These are from example 1. There are multiple different things you can use instead of these braces, but we're going to use the braces. It's what our book uses, and it's what I've always used. Okay, so that's pretty easy. Name them. If I want, we'll call this matrix A. If I want A, 3, 2, I look at the third row, followed by the second column, and that is -1. Matrix addition. I'm not going to use example 2. You can look at example 2 if you want, but I'm going to use something smaller. Example 2 is pretty realistic. That's a 7. So when I add these, I just add the things in the same place. So 2 plus 4 is 6. 3 plus 5 is 8. 7 plus -1 is 6. 4 plus -2 is 2. 1 plus 3 is 4. 12 plus -5 is 7. Yes, it is that easy. This is my version of example 2. Shows the same thing. Example 3 is going to show multiplying by a scalar. Again, I don't like example 3, so I'm going to replace example 3 with, again, they're giving a realistic one. I want one that's very easy to see what's happening. Makes that a nicer 2. So I just multiply each term here by the scalar that's in front of it, 3. A scalar is just a single number. So 6, 12, 3, -15. Now we come to matrix multiplication. This is the one that is a little tricky. Okay. So for matrix multiplication, I'm going to do example 4, and I'll teach you through the example. Two, 1, -3, 0, 1, 2. This is part A. Part B, I'm going to rename them. Times 1, -4, 0, 2, 1, 0. Okay. So here I have a 2 by 3. And I'm multiplying that by a 3 by 2. In order for this to work, these inside dimensions have to match. This does not work if the inside dimensions don't match. You cannot multiply. There are lots of matrices that you cannot multiply. Okay. So be aware of that. Just because it's a matrix does not mean you can multiply it. Matrix multiplying order also matters. This one you could do in the other order, you would get something else, but A dot B is A times B. So what I do here is I go, my result here is going to be 2 by 2 as well. I'm going to write it out. So you do row 1 times column 1. 2 times 1 plus, and I add each term together. 1 times 0 plus -3 times 1. So that gives me slot 1. So that's 1, 1, my location, row 1, column 1. Row 1 or row 1, column 2 is going to be row 1 times column 2. I'm going to add these up again. I'm just going to kind of move it down just a hair. I'll leave space, but 2 times -4 plus 1 times 2 plus -3 times 0. Now, for row 2, column 1, I take row 2 of the first one times column 1 of the second one. 0 times 1 plus 1 times 0 plus 2 times 1. And then row 2, column 2, row of 2 of the first one, column 2 of the second one. 0 times -4 plus 1 times 2 plus 2 times 0. Now I'm going to simplify this. 2 times 1 is 2 plus -3 is -1. -8 plus 2 is -6 plus 0 is -6. 2 and 2. And my matrix from multiplication is -1, -6. Okay. Part B, I'm going to call this C instead. Actually, it's still A. They used the same matrix, but they used a different B, so we're going to call that one C. This one was B. And so AC, I have a 2 by 3 here and a 2 by 2. Again, I've got to match up the insides. These don't match. These do not multiply. I'm not sure what your calculator would say if you put them in, but okay, using matrix multiplication. So a florist makes 3 different flower cut arrangements for Mother's Day. 1, 2, and 3. Each involves carnations and lilies. Matrix A shows the number of types of flower used in each arrangement. So this is example 5. So A, the first row, I'm going to give you kind of a little abbreviation as to what everything means. A lot of times matrices are used to represent actual things. Roses, carnations is going to be line 2, and lilies line 3. 5, 8, 7. So that's how many roses go in each arrangement. Okay, the florist can buy his flowers from 2 different wholesalers, W1 and W2, but wants to give his all his business to one or the other. The cost of the three flower types from the two wholesalers is shown in matrix B. So we're going to do oops, I missed. That wasn't where I wanted to put it. Wholesaler 1, wholesaler 2. So for simplicity, they're wanting to use this. And so to find the total cost of the three arrangements, we're going to do A times B. And that's going to give us a matrix of roses. And I'll show you when I get done with this, why this works. So we do row 1 times column 1. I guess I should move W2 over. This is a pain to get it right all the time. But I am going to make you do this by hand because I want you to practice and get the purpose down. So row 1, 7. So notice that we just did wholesaler 1, all the costs. Wait a second. Row 1 times column 1. I can multiply these because I have a 3 by 3 multiplied by a 3 by 2. And the result is going to be a 3 by 2. Row 1 times column 1. Why am I multiplying the number of roses times the price of a rose? So, therefore, we switch rows and columns of A to get the flowers. Oh, so this doesn't make any sense because I'm multiplying 8 roses. So what I'm supposed to do is transpose matrix A, which is a matrix operation. But what we're going to do is we're going to go AT is going to be 5, 8, 7. That would make more sense. 6, 6, 7, 4, 3, 3. So now I've got 1, 2, 3 this way, and rose, carnation, and lily. So now, when I come do this multiplication, I'm not multiplying the number of roses times the cost of a carnation. I'm doing the number of roses. So arrangement 1, so when I do row 1, I get rows. Yeah, that's what's happening. So this can give me the cost for number 1, for number 2, and the cost for number 3 from each of the two wholesalers. 5 times 1.5 plus 6 is carnations times 0.95 for arrangement 1. And 1.3 times 4 is the cost of the lilies. So that's all of arrangement 1. Now the next row down is going to be arrangement 2 times, again, we're in wholesaler 1, so 8 times 1.5 plus 6 times 0.95 plus 1.3 times 7. And then we do roll 3, 7 times 1.5 plus 6 times, nope, 7 times 0.95. So again, I'm multiplying row 3 times column 1 plus 3 times 130. And when I total that, that'll give me the cost for wholesaler 1. Wholesaler 2, I'm now doing row 1 times column 2. And then I do row 2 times column 2. And row 3. And that comes out to this matrix. And that's my A times B. If I want to know the total cost for getting all of their flowers, I can add up column 1 and column 2 because those are my two wholesalers. But I can also just look at it right now and go wholesaler 2 is cheaper because they're cheaper for every arrangement. This was 1, 2, and 3. So they should go with wholesaler 2 for their flowers. Okay, we need to talk about the identity matrix. The identity matrix is A, or I, and you can only have an identity matrix for a square matrix. And it does what's called runs these ones down the diagonal. A diagonal matrix is any matrix where the only non-zero numbers are down this diagonal from left to right, top to bottom. Has to be that diagonal. The identity matrix, again, has to be square, so 2 by 2, 3 by 3, same number of rows and columns. So A times A inverse should equal the identity matrix. It's like sine and inverse sine undo each other. Matrix multiplication order matters, except when we're talking about inverses, it works both ways. Okay. So I'm going to check that these two are inverses. A and I've got B here. So I do A dot B. And a lot of times with matrix multiplication, we define it and then we just write them like this. So now I've got 3 times 1 is 3, plus -2 times 1 is -2. And I've got 3 times 2 plus -2 times 3. Oh, wait, 3 times 2 is 6, not 3. Plus -2 is -6. -1 times 1 is -1, plus 1 times 1 is 1. So again, this is row 2 times column 1, and row 2 times column 2, -1 times 2, plus 1 times 3. And that works out to be 1, 0, 0, 1. I should also check this with BA. I can't just assume it does. But I'll tell you it works. And I'll show how to do this on the calculator and all of these operations in section 7.3. That's example 6. We're going to skip over example 7, and I'm going to show you, we'll come back to it. For matrices, we're going to talk about finding the inverse of a 2 by 2. This is the only one we're going to do by hand. You can only find inverses of square matrices. So here is my matrix. We'll call it A. We use capital A a lot for matrices. A inverse takes this thing we call the determinant. It has several applications, but it takes AD minus BC, and it's a single number. And so you're doing 1 over the determinant, which is a number that we're going to multiply everything by later. D, negative B, negative C, A. So what you're doing here is you're switching A and D's places, and you're making B and C negative. So if I want to find the inverse of this matrix, first I do the determinant. AD minus BC. Just make that neater. And then I swap A and B and negate. We got 1 over 0. That's a problem. The inverse does not exist. You will get what's called a singular matrix. Because there's division by 0. This is known as a singular matrix. If you try to take that on the calculator, you will get something that says singular. A non-singular is one where the determinant exists, or where the inverse exists. Okay, if it's a 2 by 2, I want you finding the inverse by hand. We're going to do one that works now in example 8 here. And keep that pattern handy. Hopefully you wrote it down in your notes. 1 over AD BC. Swap A and D, negate B and C. So this is 1 over 6 minus 4 is 1/2. And usually when I'm talking about an inverse, I put it into so I'm going to distribute it to everything. I'm multiplying my scalar in. 1/2 times 2 is 1. 1/2 times -1 is -1/2. -2, 3/2. And that is my inverse matrix. Okay. I'm gonna do one on the graphing calculator. It's gonna be a 3 by 3. I won't ask you to do a 3 by 3 by hand. It's kind of a pain. So to do this, second function here of this x inverse key is matrix. I'm going to edit my matrix A. I need to make it a 3 by 3. And I'm going to enter the original matrix. 1. Doesn't let me go over it like that. Okay. I just have to go down. And I just have to use my arrows to work my way around. Problem with hitting enter is it doesn't always put you where you want. I hit enter there, and that didn't do what I wanted. Okay, so I've got my matrix A. I'm going to quit out of this. Now I'm going to go back to the matrix button, and under names, I'm just going to hit enter, and that gives me matrix A there. The x-1 key means inverse. It will always do the inverse. And there's my inverse matrix. Okay. So that is finding an inverse on a calculator. I'm going to talk about a couple of applications of matrices. Example 9, reflecting with respect to the x-axis. So we're going to prove the image of a point under the reflection can be obtained by multiplying by this matrix. You don't have to know how to multiply it. You're just going to show that this works. Okay? And they're doing this kind of funny. It works either way. But okay, this is the matrix I'm multiplying by. My point is the matrix XY. Usually you would write it this way, and I'll show you that it works both ways. Normally you'd write it that way, and you can do multiple points together then. But anyways, XY times this transformation. So if I'm reflecting over the x-axis, all I'm doing is switching the y-coordinate to negative. So this equals, okay, row 1, there's only one row, times column 1. X times 1 plus y times 0. Now I do row 1 times column 2, x times 0 plus y times -1. And that equals x, is all that's left, that's the first one, -y. The order that you often do transformations in is this, and you'll get the same thing, but you'll get it in a vertical stack. Row 1 times column 1, 1 times x plus 0 times y, 0 times x plus -1 times y, x, -y. Same thing. The nice thing about the vertical columns is it lets you do multiple things. So, rotating within the coordinate system. X is going to rotate to x prime. And x prime is given by this. X cosine We're gonna use alpha for my angle of rotation plus y sine alpha. Y transforms to y prime. Negative x cosine alpha. And I'm just telling you these. No, negative x sine alpha. The book kind of just tells you these two. You are not supposed to come up with this on your own. So I want to put this into matrix form. XY is multiplied by this matrix to get that. So X times sine alpha sine alpha. This makes it easier if you're having to do multiple points to put it into a matrix. And negative sine alpha cosine alpha. And this transformation allows me to get where I'm going. This can be shown a little bit with some indifference identities. If you want to do other things, but usually just multiply that, or again, the way I think is a little easier because you can put multiple points in a matrix if you do this. If you do them this way, you can do x, y. You can do multiple points this way and get a matrix of all your points, because this is a 2 by 2 multiplied by a 2 by 3. Remember, it always rows, columns. And those inside ones match. The result, I don't think I really mentioned this before. The result is 2 by 3. Okay, that is section 7.2 on matrix algebra. Let's take some practice.